That's something that happens in CT because there's no thermal noise effects similar to what you see in MR. Okay? So if you were modeling intensities in a CAT scan, you would use a uniform distribution. Okay? So I didn't really pull these out of a hat. It's like there are phenomena in medical image processing that these things model well. MR, on the other hand, you need to model intensities using Gaussians here. And I put this picture up just to remind you that in a Gaussian PDF, the peak occurs at, anyone care to fill in? The peak value at the mean, there you go, thank you. And the expression on the right is, that's the expression for the Gaussian PDF. Everyone seen that before? This is the first time? First time, all right. Well, so if you look at, let's just look at that expression for a couple of seconds to try to get an intuition for it. It's ignore the constant to the left, okay, the 1 over square root of 2 pi. We'll ignore this part. Here, we'll just focus on the exponential. So this is really just an exponential distribution. So that gives you, at an intuitive level, that tells you that this is going to have tails. An exponential, a uniform distribution is just going to have these sharp corners. Anytime you see an exponent, you know it's going to have smooth tapering edges, whether they're going up or down, we don't know. But then the next thing you can observe is it's a negative exponential. Okay? So what that means is, if you look in the positive half of the x-axis, a negative exponential means that as you're going up in x, this is going to come down. Right? So without really knowing exactly what's in the expression on the right, just by looking at its form, you know it's something that's going to taper like that in the right half of the axis, right? That's already a lot without knowing the mean or the variance, right? So now, one thing to notice here is that a Gaussian is completely defined by a mean and a variance. Meaning that if I tell you that here's a Gaussian at the mean is 10 and the variance is 1, you can fully describe, you can draw for me the full picture of that PDF using that expression for px, right? So this is an example. It's a nice distribution where just with 2 parameters you can define all of it, right? Something I'd want you to think about is how about the uniform distribution? Can you fully define it with the mean and variance? I want you to think about that. Or just that's the idea of what is a compact distribution? Because when we're trying to solve real-world problems, we really want distributions that have a small number of parameters. Because we have to pull these parameters either out of air or from some sample. So the fewer parameters, the more compact your distribution, the more likely you are to use it. Okay? So everybody loves the Gaussian because it models phenomena which have a main thrust area and they sort of peter off nicely, which is a phenomenal number of phenomena. Right? So here, and this guy, we're going to use this to model MR intensities. In fact, to give you a preview of what we're going to do in our project is, I'm going to give you 4 Gaussians. Okay? When I say I'm going to give you 4 Gaussians, what that's going to mean is I'm going to give you 4 means and 4 variances. And I'll say the first one represents white matter, the second one represents gray matter, the third one represents tumor, and the fourth one represents whatever, skin. Okay? Then what I'm going to ask you to do is compute for an image what is the probability that that pixel, a given intensity, belongs to white, gray, tumor, or whatever else. Okay? Then I'm going to ask you to assign to it a label of the probability which is the highest. Okay, so if the probability of white matter was 0.2 and gray matter was 0.1, but skin was 0.8, you'd classify that. That is going to be your segmentation problem. That's how you're going to solve the segmentation problem. Then in the next part on the second half of the project, I'm going to show you where I got those Gaussians from. Did I just pull them out of air? And the problem of figuring out what the parameters of your Gaussians should be, we're going to do that using maximum likelihood estimation. Okay? So these words are a little bit bigger than what the concepts are. The concepts are very intuitive. If I just left you on an island with 2 MR images, how would you go about segmenting them? Most probably you would come up with a method like this. All I'm telling you is what are the formalisms that surround them. Okay? Well, I think, oh no, there's one last thing, the Bayes rule. You guys have seen this many times before. I'm just rewriting some of the variables. The first line there is the conventional form of probability A given B that you've seen in event space, discrete space here. Second, I've just rewritten that in a probability density domain terminology. If you look at the second equation there, and I wanted to get you familiar with the terms, the labels that I'm going to be using. So I'm going to read the second line out to you. The term on the left is probability of gamma I given X. That's referred to as the posterior probability of tissue class I. Bear with me, we're going to go over this in the next 2 days, okay? I'm just reading out this to you. The posterior probability of tissue class I, given that the intensity is X, okay? Tissue class, we're going to say tissue class 0 is skin, tissue class 1 is brain, tissue class 2 is something else, all right? We're going to come up with I is going to go from 0 to 3, okay? So the posterior probability that you're seeing tissue class I at a pixel intensity X. Posterior meaning you've incorporated all the information you ever had, and finally you're saying this is the segmentation label, okay? That is written as, let's look at the term on the right in the numerator. That's conditional, that is the class conditional probability. These are new terms for things you might have seen before. The probability X given gamma I, that's the class conditional probability for tissue class I. Meaning that if you see an intensity level of X, okay, and you know that you're looking at white matter, meaning you know exactly which Gaussian you need to be indexing into, what is the probability value? What is the probability density function? Okay? So the posterior, again, the term on the left, posterior probability of tissue class I at intensity X is the class conditional probability multiplied by probability of gamma I. That's the prior probability. That's a place where you can encode any number of constraints you want, such as the proximity to other structures, such as, you know, local coherence. We're not going to do that for this class. But what we're saying is probability that there's skin at this particular voxel is the probability that we're going to index into that Gaussian, see how likely is it to be skin, multiplied by some prior probability. If we happen to know that, you know, pixel location XYZ always has to be skin, then we can encode that in our prior probability right there. And then the bottom is a normalizing constant, and it's really the marginal probability. And what the next equation there just expresses what px is. That's the marginal probability of intensity x. We'll go over these more, but I just want to put this out there so you can take a look at the slide. And if you look at the last equation there, I've expressed the posterior probability by substituting the actual expression for marginal probabilities in there. I'm going to say this one last time here, and then we'll go off and do our MATLAB, is probability that skin, you know, the probability that skin is the label of an intensity value 100 is computed as follows. We'll look at the Gaussian for skin, and we'll figure out where 100 is on it. We'll get this first number, that's the class conditional density. Then we're just going to multiply it by this prior belief. We may not have a prior belief, but if we do know that skin tends to occur in 90% of the voxels, you know, we want to give it a little bit more weight. The probability of skin is just higher because we know that an MR image is mostly skin. It's not true, but say we knew that. Okay? So that's what we're doing here. And since it's a probability density function, since everything has to add up to be 1, you have to have this normalizing constant. So this is where you go in and compute the probability. You look up all the other Gaussians and you divide it by that. Okay? Just because this is important, because we're going to use it a lot, I want to show this to you 2 or 3 different times, and everybody's going to absorb it at different times. So this is going to be the gist of our segmentation process. We're going to be using this last expression over and over again, or maybe just once if we get it right the first time, to do the segmentation. All right? And this is the end of the lecture part. I don't want to give you an opportunity to disappear before recitation. So what we would do next is we have to go through and install MATLAB. Unfortunately, I didn't get a chance to install it on your machines. I apologize for that. And we can, if we do that process, I think we should be done with that in about 20, 25 minutes. And then after that we have there's a problem set one. It's a